Hello, my name is Steve Bowler, and in this video I'm going to be configuring basic OSPF principles. We're going to be going over the foundation with OSPF. There is a lot to OSPF, so that is why it is used in a lot of networks worldwide, because it is very scalable and it is not vendor specific like EIGRP, which is run only on Cisco routers and switches. OSPF can be run on multiple vendor platforms, and it can get pretty complicated real fast within OSPF. There's a lot of different things in OSPF in which you can tune. These aspects also make it very scalable and tunable. So in this lab, we're going to take a look at the basics of OSPF. We're going to take a look at how to get it running in your network. We might also take a look at router authentication, OSPF authentication in this lab. And we might also take a look at some basic summarization within this lab. So what we are seeing within GNS3, we have area 0, which is the connection between router 3 and router 4. Router 3 is using its Fast Ethernet 01 and area 0, and its Fast Ethernet 00 is in area 1 with router 2 and router 1. So we have in area 1, we have a switch. We have an Ethernet connection. We're using the 192.168.0.0/29 network. And router 2 is going to be originating the 1 and 2 networks, where router 1 is going to be originating the router 3 and 4 networks. And we're going to summarize those routes on router 3 into area 0. So we're going to take a look at internal route summarization within OSPF. There is two different ways to do OSPF summarization in OSPF. We have the area range command and we have the summary address command. The summary address command is going to be used to summarize routes that are external to the OSPF process, and the area range command is used for internal routes within OSPF to summarize those routes. So what we're going to use in this lab, we're going to be using the area range command to perform summarization, because these networks are going to be originating in OSPF. We're going to advertise these networks into OSPF. We're going to take a look also at how to advertise networks into OSPF. So what we can see is that we have two areas in this lab. We have area 0 and area 1. Again, area 0 between router 3 and 4. Area 1 is between router 2, router 1, and router 3. In this scenario, router 3 is going to be our area border router. It's going to connect area 0 to area 1. We'll take a look a little more about the ABR and the function of the ABR later. So let's go ahead and do PuTTY Connection Manager. We're going to go ahead and start the routers. We'll get on the command line and start getting some of the configuration done. We're going to create loopback 0 and 1, so we'll do the host name to R1. We'll go underline console 0. We'll set the no exec timeout. And then under interface Fast Ethernet 00, we're going to give it the IP address of 192.168.0.1, and it's we're going to give it a /29 subnet mask, which is 255.255.255.248. We'll do a no shut on the interface. We'll do the interface configurations first. So let's go under R1 and do the interface loopback 0, and we will give it the IP address. We'll give loopback 0 the 3 network, which is 192.168.3.1. We'll make all of our loopbacks a /24 subnet mask. Then we'll go under loopback 1 and give it the 4.1 IP address with the /24 subnet mask. So let's go and show you how to get under OSPF. To set up OSPF, we go under global configuration mode, and we go and type in the command router followed by OSPF, and then we do a question mark, and we're going to give it a process ID. We'll give it the process ID of 1. What we can see if we do a question mark now inside of OSPF router configuration mode, we have a lot of different commands we can do. We're going to be using what we can see with this command, area command, is that we have a lot of different options under the area 1 statement. We're not going to do this yet, but we're going to use that command later on. You can see the range statement under there, and we can also set up authentication under this. So we'll take a look at that later. Just wanted to show you that. The first thing we want to do, and usually what you do when you set up OSPF, is you want to advertise your networks into OSPF that are on the local router, or the interfaces on the router that you want to try to form neighbor adjacencies across are advertised into the OSPF domain. In this case, we're going to advertise our fast Ethernet interface, which is 192.168.0.1, and if we follow that up with a question mark, you have the wildcard bits. This is going to allow us to apply a subnet mask. So we can, with this mask, it can cover a range of IP addresses, and if those IP addresses are on the router, they will be advertised into the OSPF process. So in this instance, we'll do a wildcard of all zeros because we just want to advertise our interface with this specific IP address on it, which is our fast Ethernet 00. If I were to put in 0.0.0.255, what this is going to advertise is the 192.168.0/24 all the way from 1 to 255. Everything inside there, it's going to find it under the router on any of the interfaces and establish OSPF adjacencies across those interfaces. So what we're going to do to try to lock that down a little is only advertise OSPF on the fast Ethernet 00 interface. So that's why we're giving it a host mask of all zeros. And then you can see if we OSPF uses the wildcard bit mask, kind of like ACL matching logic as well. So if you're good with ACLs, you should be good with the network statement within OSPF. Then after the network, IP and subnet, or wildcard bit mask, we have to advertise our area. And router 1 is going to be in area 1. So we'll go ahead and hit enter, and that should be it. So now that is done, now we will go and advertise our other networks as well on R1. The other interfaces are the 3 network and the 4 network on router 1. So we'll do the 192.168.3.0. This time I'll show you how to advertise the whole /24, which is 0.0.0.255, and we will put that network into area 1. We're also going to advertise the OSPF network of .4. So that should be enough to get us going with OSPF. OSPF is a link state protocol, and it uses cost bandwidth to find the best path through the network. So it's going to prefer higher speed links over lower speed length, and it's going to assign a cost value to these interfaces based on the type of interface. So you have if you have high-speed interfaces like gig interfaces, OSPF was founded a long time ago. When it was developed, they didn't have gigabit Ethernet interfaces and those fast speeds. So what we have to do within OSPF to get we need to tweak our bandwidth statements in OSPF to get the full advantage and utilization of the gig interfaces that might be running in your network. So there is a calculation, but I'm not going to go into the detail of the calculation, but there's anything over a certain speed, it's all going to get the same cost value applied to that interface. Remember, all interfaces are given a cost value based on the speed of the link. Fast Ethernet, gig, T1, etc. So we're not going to take a look at that in this lab, but I just want to tell you about how OSPF finds the cost and calculates cost. So with what we have on router 1, we have the basic network configuration set up. If we do a show IP protocols, we can now see the routing protocol is OSPF process 1. We can see the routing that we're routing for the 3 networks that we advertised into OSPF process 1 into area 1. We also have what is called a router ID. And what we will see is that we admin up these other routers with OSPF. In an Ethernet environment, in a LAN environment, what OSPF will do is it will try to form a designated router and a backup designated router. The designated router is going to be all of the routers in the area send multicast traffic to the designated router and the backup designated router. And these routers then make decisions based on what the best path is through the network in that area. And then they forward these updates, these link state updates, out to the other routers. So these updates get sent out over another multicast address to all of the other routers within the OSPF area. So you have 2 multicast addresses which are primary within OSPF. The all designated routers and backup designated routers, and you also have the all other routers. Those updates get sent out by the DR and BDRs to all the other routers. So this way it kind of limits the updates throughout your area. So all the routers in your area report to the BDR and the DR, and in turn the DR and BDR send updates out to all of your routers within the area. So that's with Ethernet networks. We will not see that in frame relay and other network types unless we specify otherwise. Like in a point-to-point connection, we do not need a DR and BDR because there's only 2 routers on the local segment, hence the point-to-point concept. So there's no need for a DR and BDR election. So let's go back to router 1. We will do let's run a couple of OSPF debugs. We'll do a debug IP OSPF packet on R1. And let's also do a debug IP OSPF events. So now that we have a couple of OSPF debugs on R1, let's go to router 2. We can see that we have commands already coming back. Sending hello out 224.0.0.5 to area 1. Out it's fast Ethernet 00. So again, if we look back, if I do a show IP OSPF neighbor, I do not have any neighbors yet formed. So what we can see though is that OSPF is already trying to establish neighbor adjacencies with other routers within the area. So let's go into router 2 and get router 2 configured. 224.0.0.5 is the all DR and BDR multicast address. So it's trying to communicate right now with the DR and BDR, router 1 is, by sending them those hellos out. Let's set the host name. We'll go under line console 0, set that up. We'll also go under interface fast Ethernet 00. Again, router 2, we're going to give the .2 IP address with the /29 subnet mask. We'll go under loopback 0. We'll give it the IP address of, on router 2, it's going to be 1.1 with the /24 subnet mask. So right now we're just getting the interfaces set up on router 2. We'll go under loopback 1 and give it the we'll put it in the 2.1 IP address and then /24 subnet. We'll go under router OSPF 1. And the next thing we're going to do within OSPF process 1 on area 2, we are going to do the network statement to advertise our networks into OSPF. In this case, we're going to advertise 192.168.0.2 with the wildcard bit mask of all zeros. This is the host bit mask. So it's only going to send hellos out the interface on the router that has this IP address. And then we're going to specify area 1. And then we will also advertise our other networks, our loopbacks, which are network 192.168.1.0. We'll do a /24 wildcard bit mask, put that in area 1, and we will also put the 2 network in area 1 as well. So first, what you can see is we have an OSPF adjacency change for process 1. We have a neighbor of 4.1. I'm sorry, we have a neighbor now with, yeah, that's correct, 4.1 over fast Ethernet 00. So if I do a show IP OSPF neighbor, we have a neighbor ID which is router 1, which is 4.1. The priority is set to 1. The state is full. We can see right now that router 1 is the designated router on the local segment. We have our dead time interval, our dead timer, and we also see our address of router 1 in which it established the adjacency on. So now on router 2, if I do a show IP protocols, we are seeing the networks that we're routing for. We can also see under routing information sources, we are seeing the gateway of router 1. We can also see our router, local router ID. And what we can do to change this, and to be a little more clear on the router ID, let's go ahead Well, let's think about this for 1 second. If I want to show you this in the lab, what we can do is create our router IDs to kind of match like the router numbers. So like router 2, we could create a router ID of, we could specify, if we go to under router OSPF 1, we can set the router ID for the OSPF process. We can give the router ID of 2.2.2.2, and we'll go back to router 1 and give it, under OSPF process 1, we'll give it the router ID of 1.1.1.1. And then to clear the OSPF process, we'll do a clear IP OSPF process, then hit enter. We have to specify yes under here for the OSPF neighbor to clear the, for the OSPF router to clear the process. We'll take off all the debugs right now. We can also do a show debug to see what debug commands are on your router. What we can see is OSPF is a very chatty protocol, converges very fast. That's why the hello dead timers are set so low. Going back to the designated router and the backup designated router theory, if the designated router were to fail at any time, the BDR, or the backup designated router, holds a snapshot of the whole area, links all the networks within the area and the best path to reach them. So it has the same map topology as the designated router. So if the DR fails, the BDR will be able to come online and forward traffic immediately with no time lost. So this is in an Ethernet environment. When I cleared the process on R1, we flushed all of our links. The DR-BDR election, you can see, was taking place. What we can see is that we have elected the DR. If I go to R1 and do a show IP OSPF neighbor, if I do a show IP protocols, we can see that now we have a router ID of 1.1.1.1 on R1. So this has changed when we cleared the OSPF process. If we were to go to router 2 and do a show IP protocols, we can see that on R2 this router ID did not change. And I believe it probably did not change because I did not clear the process on the OSPF process on R2. So let's clear the process on R2. Clear IP OSPF process, hit enter, and then hit yes. And now we can see the correct process ID has changed. So if I do a show IP protocols on R2, our router ID has now changed to 2.2.2.2, and on R1 now you can see that we are in good shape. So if I go on R1 and do a show IP OSPF neighbor, we can see now that we have a neighbor ID of 2.2.2.2. So what we can see that router 1 in this scenario is the designated router, and we can see that router 2 is the backup designated router. Again, the OSPF process we can use, the router ID is used to communicate between the routers. The highest router ID is going to win as the designated router in most cases. If I go into R2 and do a show IP route, we have routes that we have learned via OSPF. We're seeing the 4.1 and 3.1, which are the connections on router 1. Let's go ahead and try to ping those and see if we have layer 3 reachability. So now we have reachability to those OSPF networks. Another thing to mention is that OSPF's administrative distance is 110 by default. That is the cost to these links. And you can see the metric of 2. So let's go to router 3 and get it configured, and then show you a little bit more about OSPF. So again, the router ID is used a lot of times in virtual link applications within OSPF. We're not going to take a look at virtual links in this lab, but the router ID, you usually want to make a loopback interface. That way it's not as hard-coded as a physical interface and will go down. You don't want your router ID to change, because that could be traumatic within your OSPF domain. And also, if you have your router ID hard-coded when you're doing virtual links, if you are doing that, if it's hard-coded, that way if a new router, if you put in a new interface, a loopback interface on your router, and it is higher than the loopback that you have it configured for previously, that will break your virtual link connection. So, because again, OSPF will find the highest usable available IP address on your router to have the router ID. So now on router 3, we went ahead and gave it the host name. We went under interface FA00. We gave it the .3 IP address in the /29 subnet mask. And then we went under fast Ethernet 01. We gave it the IP of 100.3. And then our next step is to go under router OSPF 1 and give it the IP address of network 192.168.0.3. We'll give it a host mask and put this in area 1. So what we should see now is we should form neighbor relationships with router 2 and router 1. The next step, what we could do is give it, again, best practice within OSPF is to hard code the router ID. In this case, it's going to be 3.3.3.3. And then we're going to go ahead and clear the OSPF process. We'll go ahead and clear the process on all the routers at the same time. So again, the router ID is a very important concept you need to learn to understand. Again, it's going to find the highest loopback interface, and then if there's no loopbacks, it's going to find the highest IP of the interfaces that are in the up state on the router to calculate the router ID. Highest IP address. So now if I do a show IP OSPF neighbor on R1, we're seeing the state of two-way druther. So what we can see is OSPF taking a minute to converge. From R1's perspective, what we are seeing, router 3 as the designated router and router 2 as the backup designated router. So again, the highest IP address is the DR. If I do on R3, if I do a show IP OSPF neighbor, we see router 2 as the backup designated router, and we see router 1 is neither a DR or BDR. It is a druther. It is just another. It's not the designated router and it's not the backup designated router. It's just another router in the OSPF network. So at this point you can see how the election process works within OSPF. It sees router 3 as having the higher IP address. So router 3 is going to win the election and become the designated router. Router 2 has the second highest router ID, which is 2.2.2.2, and then it becomes the backup designated router. And router 1 comes in last place with 1.1.1.1, so it's neither the DR or BDR, it's what's called a druther, or DR other. So let's do a debug on OSPF on R3. Let's do a debug IP OSPF packet and a debug IP OSPF events. And we can see that we are sending hellos to 224.0.0.5. So what we can see is that we're sending hellos to 224.0.0.5 area 1 on fast Ethernet 0.0. So from the DR we are sending these hellos out to the other routers. So we're just making sure that we have a relationship still with the designated router and the backup designated router. We're still just making sure that we have that relationship there. If I do a debug IP OSPF events on R2, we've seen that we are receiving hellos from router 3. Again, it's sending hellos on 224.0.0.5. So it's sending hellos back. So the DR and the BDR are talking to each other over this multicast address. That's for the BDR and DR to talk on. Because remember, they have to have the same link state topology. They have to know where all the best paths are through the network from their point of view. So the designated router is sending an update out, the multicast address of 224.0.0.6, which is for all the other OSPF routers. If indeed there was something new inside of OSPF that changed, then it needs to send an update out. But right now we're not seeing that, we're just seeing the traffic to and from the BDR and DR. So the next step now, and what we need to remember, in OSPF, all the areas have to connect to area 0. Area 0 is known as the backbone area. So router 3, if it's going to have interfaces in area 1, it's also going to have at least one interface in the backbone area, which is area 0. So with that being said, router 3 does indeed have another face in area 0, which is Fast Ethernet 01. So if I do a show run on router 3, if I do a show IP interface brief, we can see Fast Ethernet 01 has the 100.3 IP address. We'll go under router OSPF 1, and we're going to now advertise this IP address into area 0, again with the host bit mask. And now let's go to router 4 and get router 4 configured to be configured in area 0. And once we do that in area 0, we have created our backbone area between router 3 and router 4. So let's get the host name set up. We'll get the line console 0 set up. We'll do the interface Fast Ethernet 00. We'll give it the IP address of 100.4 with a /29 subnet mask. We'll do a no shut on the Fast Ethernet. And then the next step, we'll go under router OSPF 1, and we're going to give it the router ID of 4.4.4.4. And then we will follow it up with the network statement. So we're going to advertise 192.168.100.4 with all zeros under area 0. So again, any interface with this IP address, we're going to start sending hellos out, trying to form neighbor adjacencies. And we can see that we just have formed a neighbor adjacency. If we do a show IP OSPF neighbor, we have a connection with router 3 now. And it sees router 4 sees router 3 as the designated router. If I do a show IP route on router 4, you can see now that we have some OSPF routes that we have learned, and you can see that all of these routes, the 4 network, the 1 network, the 2 network, all of these networks are showing up as of OIA in our routing table. So these are what's called inter-area routes, so that this router has learned of these routes in a different area that it is in. Remember, router 4 is in area 0 specifically, and that's all. So that's why these come up as OIA in router 4, because these routes originated in area 1. If I go to router 3 and do a show IP route, yeah, we have a problem. All these routes come up as /32. So the next thing I want to show you is something that's not really a problem, really would be a problem in the real world, but when you are configuring loopback interfaces, if I do on R2, what I'm going to show you is, if I do a show interface with loopback 0, we configured all of our loopbacks, if you remember, as a /24. However, if I go under, if I do a show IP OSPF interface loopback 0, the network type is loopback. And that is because by default, if I add a loopback interface into OSPF domain, they're going to come up as network type loopback. And even though you might put a /24 on the IP address, what we can see on the routing table in the other routers as it's coming up as a /32 subnet. So what we need to do to change this default behavior of the loopback interfaces within OSPF is go under the loopback interfaces and do the OSPF command, which is IP OSPF Network, and then we just need to change our network type on the loopback interface. So we'll just do IP OSPF network, I'm sorry, not broadcast. What we're going to do is advertise these as not broadcast. We're going to advertise these as point to point. Let me just verify something real fast. So again, they're coming up as /32s in all the routers routing tables. We need to change this default behavior so that the correct subnet mask is advertised to all the other routers. So again, to change this behavior, we had to go under the loopback interfaces and change the OSPF network type. So we'll go under interface loopback 0 and we'll do IP OSPF network point to point. So with that being said, I put that command under that loopback, again with the following command, IP OSPF network point to point. So now if I go to router 3 and do a show IP route, for the one network you can see now that the correct subnet mask is now showing up in the routing table, because before it was a /32. And now we can also see the 2 network as well coming through as a /24. But the 4 and the 3 networks are still /32s. So let's go ahead on to router 4 and change that behavior as well. We will go to the loopback interfaces and change the network type. We'll do that with the IP OSPF network point to point command, and then we'll go under loopback 1 and do the same command. And that should be it. If I go back to router 3 and do a show IP route, it's still seeing a /32. It's going to take a minute for the next link state update to come through, and it should change in 1 second or 2 seconds. Let's do a show IP OSPF neighbor. We can see that we have adjacencies with router 4, 1, and 2. Let's go to router 2. If I do a show IP route, it's still seeing it as /32s. Let's do a show IP OSPF interface loopback 0. Let's go to router 1 and do a show IP OSPF interface loopback 0. Did I do it on the wrong router? I'm sorry about that. Looks like I went under the wrong router and did that. Let's go under router 1 and do it under the correct interfaces. That might help. So under router 1 we'll do interface loopback 0. We'll do IP OSPF network point to point, and then under loopback 1 we will do the same thing. So if I do a show IP interface brief, I do have the correct IP addresses on the loopback interfaces. So which router did I configure? I must have done that on router 2. Did I do that on router 3? No. So sorry about that. Sorry about the confusion. So now if I do a show IP route on R3, we are now seeing the /24s, the correct subnet information being sent now with the 3 and 4 networks. So again, if you're seeing /32s, go into your loopback interfaces and change the network type from loopback to point-to-point to change that default behavior if you're not seeing the correct subnet mask information being sent throughout your OSPF domain. If I do a show IP OSPF database, what this command will show us is the different type of LSAs being sent out between our areas. And this is going to give us a lot of good information. We will get more into this command later on when we get into the different OSPF network types. We'll take a look at this in more depth. You can have a stub area, you can have a total stubby area, you can have a not so stubby area type. There's a lot of different area types, and I have a lab, an OSPF lab, that shows you guys and goes over all those different types of areas. So if you want all that information, I recommend watching my other OSPF video, and I will give all that information to you in that lab. So in this case, if we don't have any other links out to anybody else, but we could set this up as maybe a stub network or a totally stub network, because we don't have any other links out to any other routers except for the one through router 3, because our LSA traffic needs to be limited and there's not really that much else inside of area 1. So we could use a stub network or totally stub network to filter out some of that unneeded LSA traffic from entering into area 1. So these two routers, router 1 and 2, are called internal area routers, where router 3 is called an ABR, or area border router, because it borders area 1 and area 0. It has interfaces in both areas. So router 3 is an ABR, and router 4 is strictly a backbone router. So there's three router types here. There's a backbone router, which is router 4, an ABR, which is router 3, and then we have router 1 and router 2, which are internal routers inside of area 1. So let's go to one of the internal routers. If I do a show IP OSPF database, it only sees link states within area 1. We have the link IDs, so it sees the router. These are considered router LSAs, which are LSA type 1s, which all the routers in the area send out. So they all know how to get to each other. LSA type 2, which are netlink states. This will tell us LSA type 1 is a router, and LSA type 2 is going to give us the designated router within the area. So it lists which routers are joined together on the segment. So in this case, router 3 is the router. It does this by the link state ID, or the router ID of the router. So this IP address, the link ID, which is 0.3, which is the fast Ethernet interface pointing out towards R3, which is the advertising router in this case. So this is the network LSA, LSA type 2, and the summary LSA is the type 3 LSA, and And what we can see is the summary LSA is used by the area border router. It can take a lot of prefixes learned within the areas and summarize them. So again, this is a very quick look at the Show IP OSPF database. We're going to hit more on this command in a different OSPF lab that I have. We can see we have multiple areas on R3 because it is the ABR. We're seeing these LSAs in both area 0, and also we are seeing LSAs in area 1. So very good information, very detailed information that you're going to need to know if you want to master OSPF. I have a lab on all of this already, into looking at all the different LSA types, the different area types, and explaining all of those concepts. So again, all these topics are explained in a different OSPF lab that I have already available to you. So in this lab we want to stick back to, we're going to maybe be doing internal route summarization within OSPF, within our network. And we're also going to take a look at, if we have time, we're going to take a look at OSPF authentication as well. So the next step, what we want to do after taking that brief look at the Show IP OSPF database command, we're going to go back to area 0. We see that we have two fast Ethernet, we have router 3's fast Ethernet 01 and router 4's fast Ethernet 00 connected together to create area 0. We also see router 3's other interface, fast Ethernet 00, which is connected into area 1 along with R1 and R2. If I do a show IP route on R3, it sees all of the OSPF learned networks. It sees all those as regular OSPF networks, intra area. Now if we go to router 4 and do a show IP route, we're seeing OIA routes are inter-area routes, because router 4 only knows of area 0, where router 3 knows of both area 0 and area 1 because it is the area border router, or the ABR. So what we can see is we have a lot of routes in router 4 within its routing table. We can do internal OSPF route summarization performed on the ABR to scale down and limit the size of the routing table on the routers without breaking connectivity or reachability. We do this if we go to router 3, and we'll go into router OSPF 1, and we will do the command area, and what we are going to do in this situation is we're going to do area 1 followed up with the range command, and then we will type in the range of IP. So what we've learned in area 1, we've learned the 1 network, the 2 network, the 3 network, and the 4 network. So in this case, we're going to run into a problem. I can see us running into a problem trying to summarize with our current networking topology. If I try to do a if I try to summarize using 1, 2, 3, 4, we will do this. I'm going to change some of these IPs real fast, and then we'll do some summarization. Okay, so if I would have tried summarization on that block of IPs that we had, the 1, 2, 3, 4 network, I would not have been able to summarize all of those within these same, with the correct subnet. So what we're going to do is, and what I did was I changed the IPs, the networks, to 4, 5, 6, and 7. So if I go back to router 1, you can see that it is originating the 4 and the 5 network, and router 2 is originating the 6 and 7 network on their loopbacks. So if I do a show IP route on R4, you can see all those inter-area routes learned from area 1, so 4, 5, 6, and 7. So say I want to summarize all those. Correctly, we're going to summarize those routes into a, not a /30, but we're going to summarize all those into, let's go into router OSPF 1. We'll do the command area 1. We'll do the range command, and then we'll do 192.168.4.0, so which is our network. And then our subnet mask is going to be 255.255. So it's going to be 255.255.252.0, because 252, this is a going to be a /22 subnet mask. This is going to allow for 4 networks to be summarized. The 4 network, the 5, the 6, and the 7 networks are going to be covered with this subnet mask. If I would have tried to put this 252 on the area 1 range with the 0, 192.168.0.0, I would have only been able to summarize 0, 1, 2, 3 networks, so that 4 network would not have been able to be summarized. So that's why I went ahead and changed the IPs so that we can make the summarization a little better with one command. We're doing the area 1 range 192.168.4.0 with the /22 subnet mask, which is 255.255.252.0. Again, this is done on the ABR, the area border router, and this is internal OSPF route summarization. So now if I do a show IP route on R4, instead of 4/24s, I have 1/22, which is what we plan to do with our summarization. So I can ping the 4.1, we can ping the 5.1, the 6.1, and the 7.1. So this is how you successfully summarize within OSPF routing domain. Within the OSPF routing domain, we use the area range command that is configured on the ABR for internal route summarization. We specified the area in which we wanted to summarize in. We want to summarize the area 1 routes in the range, the network range that we want to summarize, which in this case was the /22 with the 4.0 network. So if you want to do summarization on external routes that are not originated within the OSPF domain, we use what's known as the summary address command. And I do have a lab on external route summarization, so you can check my other OSPF videos for a lab on that as well. So now if I do a show, so let's see, on R3 I'm not seeing anything different. Actually, we should see the, let's look on R4. If I do a show IP OSPF database, we are seeing the 192.168.4.0 network as the link ID. In router 4, we are seeing the summary net link state of 192.168.4.0. So again, that's just a quick look at the show IP OSPF database command. The advertised router that is giving this to us is router 3. So with LSAs, it gets very complicated very fast, and so that is why I have a video just on the link state, advertisements, and all the different area types within OSPF. There is a lot to OSPF, and that is why OSPF is so important to know, because it's highly scalable. There's a lot of options with it, and I mean that's why they test for it on the CCNA all the way up to CCIE, because you must know OSPF very well within all of your studies and in the real world, because it is implemented all across the world in many networks. So let's go to router 4 and set up some debug commands. We'll do debug IP OSPF events. I think that should be enough for now. On router 3, there is two different types of authentication within OSPF. There's plain text authentication, where the passwords are going over plain text and you can sniff that traffic and get those passwords, or you can do it a little more secure, which is by using MD5 authentication with your OSPF, between your OSPF routers. So let's show you some authentication within OSPF. We will go under interface Fast Ethernet 01 on R3, and we will do the command IP OSPF Authentication. We'll follow that up with the key command. So we'll do IP OSPF Authentication key, and then we will supply the key or make the key or the password as Cisco. So now if I do a show IP OSPF interface Fast Ethernet 01, let's see if we can see. Okay, we don't see that information yet. If I do if on R3, if I do a show IP OSPF neighbor, we can still see that we have a neighbor adjacency with R4. We can see the dead timer resetting. So I have my key set up. So under Fast Ethernet 01, now that I have my key set up, I go under the interface and do the IP OSPF Authentication command. So now if I do the show IP OSPF interface Fast Ethernet 01, we have simple password authentication enabled on the interface. And if I do a show IP OSPF neighbor, you can see that my dead timer is coming down now. I'm not sending hellos out every 10 seconds now. My dead timer is about to expire, and my neighbor relationship is about to drop right about now. And you can see my adjacency has changed. My neighbor relationship has changed with R4. So we are no longer peering with R4. If we do an unall on R4, turn off the debugs, we can see that the dead timer has expired and the OSPF neighbor adjacency has gone down. So if I do a show debug, let's do an unall and turn off all the debugging. I thought I already did that. So now that we are receiving packets from router 3 and we are getting the error mismatch authentication type. So what this is basically saying is that they have authentication set up and we do not, so we will not form a OSPF neighbor relationship between R4 and R3. So let's go to R4 and set up authentication on it as well. We'll do that with the IP OSPF Authentication command, and we will give the key BBBB, and we will put in IP OSPF Authentication on the interface. So again, two commands, the one specifying the key and the other one is just specifying OSPF Authentication. So we purposely put in the wrong password just to show you another error message that you might get. We are getting a mismatch authentication key clear text indication now. So the problem now is that router 3, if we do a show run, we have a key of Cisco. If we want to encrypt these passwords on the router, we'll just do a service password encryption. Now we can see that that key that was plain text before is now hidden or encrypted. So it's kind of safer just in case someone's just walking by, sees passwords, I don't know, or someone got a hold of your running config. They can still crack that encryption, but it just provides a little more level of security rather than having the password shown in plain text. So that's just one way to encrypt your password using the service password encryption command under global configuration mode. Most of you probably already know of this command and are well aware of its capabilities. So what we can see on R4, it's still not authenticating. Let's take debugging off. R4. We will go under interface fast Ethernet 00 on R4, and instead of giving it this key, which is the wrong key, we'll do the IP OSPF authentication key Cisco. So now what we see immediately is we're seeing the OSPF neighbor relationship now has come up. So if we do a show IP OSPF neighbor, we can see now that we are peering with R3. To verify that you have it enabled, do a show IP OSPF interface on the interface you're trying to set up authentication on. You should see a message at the bottom saying simple password authentication enabled. So let's go back under interface fast Ethernet 01 on R3. I can do the command IP OSPF Authentication and give it the authentication key. I'm sorry. If I do the IP OSPF message digest key with the key of 1, we can specify 255 keys if you want. We'll just do key 1 MD5, and then we'll specify our password, which is going to be all uppercase Cisco in this case. So now if I do a show IP OSPF interface FastUthernet 01, you can see it's still showing simple password authentication enabled. So let's go back under the FastUthernet 01 interface, and we'll do the command IP OSPF Authentication. Now we can specify message digest, our MD5 authentication on our interface. So now if I do look at the interface again, you can see that the authentication has changed to message digest authentication, and it's given us our key ID. You can see now that our dead time is counting down to R4. So MD5 authentication is going to trump plain text, our simple password authentication across the link, as we can see. Our neighbor adjacency is about to die to router 4. So now that our dead timer has expired, we no longer have a OSPF adjacency to R4, because R4 is using simple password authentication, whereas R3, if we look at the interface again, the OSPF interface, we are using message digest authentication, and the youngest key is the only one that we have available, which is key 1. So to fix this problem and to set up MD5 authentication, we will go under interface FastUthernet 00. We'll do the command IP OSPF message digest key 1, and then we're going to specify MD5 and then configure our correct password, which is all uppercase Cisco. And then we're going to also specify our other command that is very important, which is IP OSPF authentication message digest. So before, where we just hit enter after authentication, we are using message digest at the end to specify MD5 authentication. So once I hit enter, we can see that our OSPF neighbor adjacency has come up. If I do a show IP OSPF interface under FastUthernet 00 on R4, we can see MD5 authentication enabled with the key ID of 1. So OSPF authentication, this is a quick look at getting authentication configured on OSPF on a per interface basis between two routers, router 3 to router 4. We went over a couple of different OSPF area types. We took a look at LSAs. We looked at the BDR and DR election process. The highest loopback IP address, or the highest IP address on the router, is going to win the election. If there's no loopback, it's going to be the highest IP address on the physical interface that is in the up state. So those will take priority and try to become the designated router. We can also specify our router ID, hard code the router ID within OSPF. That's a best practice. By default, the router ID, if we do not have it specified, it will be the highest IP address on the router. So it's going to try a loopback, and then it's going to try the highest IP address of the physical interfaces that are in the up state. We also looked at how all OSPF areas that are not area 0, how they have to connect to area 0 via the ABR. We're going to talk a little bit of way you can bend this rule and get around this, so using virtual links and GRE tunnels, which I have a lab on that too as well that you can take a look at to get a way around this default rule in which every area has to connect to the backbone area, which is area 0. So say we add down in our diagram, we add another router. We can set up area 2 to where it's directly connected to area 0 if we add another area down here by what's called the virtual link. We'll get into that a little later on into a different lab. Actually, I have a lab on that already you can look at and watch. So again, this is just the basics of OSPF. This is going to give you guys a solid foundation and understanding of OSPF and how OSPF works, how to configure it, how to verify the operation of OSPF with show and debug commands. There's multiple ways to tune OSPF. But the main thing is to remember within OSPF is that it is a great protocol that is highly scalable, and that it can be, and there can be a lot done with OSPF. So thanks again for watching this video. I hope you learned a lot, and I hope to see you guys in the next video. Thank you.